In this video, we're going to be going over lesson 2.2. This is supposed to be viewed after you finished completing that table that was uploaded onto iLearn. So once you finish that and you want to check your answers, then continue watching this video. But if you have not yet finished watching this, if you have not yet finished this worksheet, then I suggest that you continue trying it out. So the worksheet that I'm talking about is this worksheet right over here. And we're trying to determine these key characteristics about the 6 trig functions that we're focusing on. So sine, cosine, tangent, and then the quote unquote inverses of it. They're not really inverses, but I like to call them inverses. Okay. So when we look at the graph of sine of x, right, we understand that it is related to the unit circle, right? So as we continue advancing through the different angle measures within the unit circle, we see that we actually create this sinusoidal wave, right? And in order to complete one full wave, that corresponds to one full revolution around the unit circle, right? It goes all the way up to 2 pi, right? And so if I'm trying to explain what does my graph look like, right, I would say that it looks like a sinusoid. And then there's another key characteristic about sine that we don't really have for our other sinusoidal wave, cosine, right? When we look at sine, we notice that it must pass through this origin point, right? If it does not pass through this origin point, then you're not working with sine of x, right? So another key characteristic of what it looks like is that it passes through the origin. Now we can talk about like, oh, what if you do a vertical shift up or down? Then would it pass through the origin? No, right? But then in general, if you're talking about the parent function of sine of x, it passes through the origin, and that's how you can differentiate it between sine of x and cosine of x. Now, another thing that we want to explore is whether or not this has any asymptotes, right? And when we're talking about asymptotes, we're talking about whether or not the function shoots off in one direction forever and ever and ever, getting infinitely closer to it, but not ever really approaching it. And when I look at sine of x, right, if I zoom out as much as possible, it doesn't really ever shoot off into infinity without ever fully approaching a value, right? And so because of that, we know that there are no asymptotes for sine of x, right? It is a continuous function. There are no discontinuities. So any asymptotes? No. Let's look at the domain. So when we're talking about the domain, we want to identify, are there any values for which our function does not exist, right? Or if our function has any asymptotes. We already established in the last part that we don't have any asymptotes for sine of x. And so we want to establish whether or not we can actually continue for all real values for this function. And if I keep zooming out, right, looks like this function goes on and on and on the left end and on the right end. So because it has an infinite f of x value for, oh sorry, not an infinite f of x value, but it goes on for infinity on the right hand side, and it goes on for infinity on the left hand side, we can establish that the domain for sine of x is all real values. And we're specifying real because we're not graphing on a complex plane, we're only graphing on a xy real plane, right? Our range is asking us what are the possible outputs or what are the possible y values. So I'm gonna zoom in a lot furthermore. Go in, right? And we notice that the highest point that our function reaches is at 1, and the lowest point at which our function reaches is at -1, right? So we can establish that the range is going to be including -1 and all the values between -1 and 1, right? So that's why I put the bracket sign outside parentheses. And as we established before with this cool graph that shows the unwrapping of the unit circle to form the sinusoidal wave, our period is going to be 2 pi. And I know this because that's how long it takes for me to create a full wave, right? And then whether it's even or odd, right, there is a really crucial test that you can do in order to identify whether it's even or odd. So the first thing is if it's even, then it has symmetry over the y-axis, right? So if it has symmetry over the y-axis, then we know that if I were to isolate or highlight the portion of my wave that is greater than 0, so I'm going to do x is greater than 0, this curve over here should look exactly the same as this curve over here, right? Because it does not, right, we have that this curve is below the x-axis and this curve is above the x-axis. We know that this is not symmetrical over the y-axis, right? So we know that this is not going to be an even function. We do know if it's going to be an even function if we rotate it around the origin 180 degrees. So let's do that. So in order to do that, we need to negate our y, and we also need to negate our input x, right? And because when I do that, I create a function that directly overlaps my original function, f, right? I know that I've created an accurate rotation around 180 degrees, and that because it directly overlaps my given function, I know that there is symmetry around the origin at 180 degrees. So it is going to be odd, right? If it doesn't pass either of those tests, it's neither, right? You can also be neither. You don't have to necessarily be even or odd. Okay, let's explore cosine, right? So same kind of thing. If I were to unwrap my unit circle, I notice that I can unwrap the entire rotation around the circle and create my first sinusoidal wave. So this is also a sinusoid. This is one of our sinusoids, right? And it does not pass through the origin, right? And that's a key difference between cosine and sine, where sine does pass through the origin. So any asymptotes, cosine looks really similar to sine, right? We established that when we were trying to differentiate between sine and cosine. And it just is a continuous function, so doesn't necessarily have any asymptotes. So no asymptotes, right? Doesn't shoot off into infinity in one direction or the other. And just like sine, right, the domain is going to account for all real values of x, right? So this is going to be all real values. The range for cosine, if we zoom in even further, right, is actually going to be the same as sine of x, right? Because this is just the y value of those of those terminal points around the unit circle. So I see that my highest y value is 1, my lowest y value is -1, so I'm going to create this interval, -1 to 1. And just like before, right, we noted that in order to form the full wave, right, we need to just unwrap the unit circle entirely, so that's going to be 2 pi. And I'm going to shift this over here, right, so that I see the left-hand side of my y-axis and the right-hand side of my y-axis. And so let me see if this is an even function. So I'm going to do this by checking whether or not this right-hand side looks exactly the same as my left-hand side. And because it does, right, I see that there's symmetry about the y-axis, so I know that this is even. Okay. Now let's go through tan of x, right? So tangent of x, if I unwrap this around the unit circle, oh, okay. What do I notice, right? I see that there's this boundary line being formed. And so because there's this dashed boundary line being formed at x equals pi over 2, I know that there is an asymptote at x equals pi over 2. So I'm going to say that this is when we have x equals pi over 2, I see that there's an asymptote there. And let me see if that continues on, right? Oh, okay. Another boundary line right over here at 3 pi over 2, right? So at x, whoops. There's another one at x equals 3 pi over 2, right? And if I were to wager a guess, I would say that there's another one at 5 pi over 2, at 7 pi over 2. And so I think that I can actually start generalizing this, right? I can generalize that whenever we have pi over 2 and we're adding, let's say 1 pi, like, right? Times any value, so times like n times any number, right? We're gonna end up getting the x value for an asymptote, right? And so we know that this is a periodic function because we see that this kind of wave pattern is continuing on and on and on, right? But we know that it's not a sinusoidal curve because it doesn't follow that sine of x, cosine of x design, right? And so if we have vertical asymptotes like how we have over here, right, we know that it's going to be all real values except those x values at which our asymptotes occur, right? So it's going to be except when x equals pi over 2 plus 1 pi times n. Our range, we see if we zoom out, let me actually zoom out over here. If I zoom out all the way over here, right, I see that I go off into infinity, positive infinity, and negative infinity. So my range is going to be negative infinity to positive infinity. And I put parentheses because I could never really reach infinity, right? my period, how long it took for me to get one little shoot off, right, was going from pi over 2 to 3 pi over 2, right? This is my full wave, right? So the difference between 3 pi over 2 and pi over 2 is just 1 pi, so my period is just going to be 1 pi. And if I check, right, so if I zoom in a little bit further, and if I have my y-axis highlighted, right, then I see on the right-hand side, right, this is not looking symmetrical to the left-hand side, so I know this is not even. Let me check if it's odd. So I'm going to negate my y and negate my x. Oh, and I get an overlapping curve, so I know that this is going to be odd.